In this presentation, we will see some guidelines related to asymptotic analysis. So let's get started. Here is the first guideline related to loops. Let's say we have a for loop which runs from 1 to n. We need to evaluate how many times this statement has been executed which is within this for loop. This is our task. We need to evaluate how many times this statement has been executed. This is the way we are calculating the time complexity, right? We know that loop executes n times. So is the statement. This statement also executes n times because this statement is within this for loop. As this loop runs from 1 to n, this statement also executes n times. So it is clear that total time will be big O of n. Obviously, I am assuming that this statement is taking a constant amount of time. Then definitely the total time will be big O of n, right? Here n means the growth is linear. Now let's see the second guideline. The guideline related to nested loops. Here is the one. We have two for loops, right? And we don't have them separately. We have this in the nested form, which means that one loop is within another loop. Here you can clearly see we have an outer loop, then within that we have another loop. This loop, which is the outer loop, runs from 1 to n, and the inner loop also runs from 1 to n. And within this inner loop you have a statement. You need to evaluate how many times this statement has been executed. Outer loop executes n times and inner loop also executes n times. Apart from this, we also know that for I is equal to 1, the inner loop runs from 1 to n. For I is equal to 2, inner loop again runs from 1 to n. For I equals to 3, inner loop again runs from 1 to n, and so on. So from this idea, it is clear that total time will be n into n, that is order of n square. So the growth is quadratic in this case. So nested loops can be handled in this way. This is how you're getting a quadratic growth because this is n into n, right? For each value of I, this will execute n times. So that is why it is n into n and this gives order of n square. Now the third guideline, the consecutive statements. We have these consecutive statements one by one. You can see that we have these statements like I have declared an integer variable x and I have assigned a value 2 to it. Then I have declared an integer variable I. Then what I'm doing here is I'm incrementing the value of x. Obviously the total time in this case will be 3 units because each statement executes one time and there is no loop in this case. Then definitely total time will be 3 units. Now talking about this loop, obviously this loop executes n times. No doubt about this. We will calculate the time separately, okay? After that we have this nested loop which obviously runs n square times. Then the total time will be n square units, right? Now what you have to do in the case of consecutive statements is that you should add all these times, right? Then it will give us the total time. This will be n square plus n plus 3, isn't that so? Then obviously this will be big O of n square or order of n square. The time complexity of this particular code is order of n square. Why is that so? We already know how to calculate the time complexity. We have fn is equals to n square plus n plus 3. This is the function under consideration, right? Let's take gn equals to n square. I'm assuming this will be the upper bound. Now the question again is fn equals to big O of gn? If that is the case, then definitely order of n square will be the time complexity. We'll compare fn and gn. We'll choose some value of c. Let's take c equals to 2 because in this case, this is just n square. I am just taking one higher value than this. This is 1 into n square. I will take it 2 into n square here. Then the inequality becomes n square plus n plus 3 is less than or equal to 2 into n square, right? Now we can solve this for n. This will become n square minus n greater than or equal to 3. We can take n common from here, then it becomes n into n minus 1 greater than or equal to 3. Finally, we will get these two inequalities, n greater than or equal to 3 or n greater than or equal to 4. So it is clear from this fact that fn is less than or equal to c dot gn for all n greater than or equal to n naught, where c is equals to 2 and n naught is equal to 3. You can take n naught equal to 3 or n naught equal to 4, doesn't matter. But here I am taking the lesser value. So for these two constants, we can say that fn is less than or equal to c dot gn, right? So we can clearly say that fn is equals to big O of n square. This is the quadratic growth, right? That is why we are getting n square over here. And obviously you can see the dominating term is n square in this case and the rest of the terms after some time will get negligible. So it is clear that fn is equals to big O of n square. So the time complexity, that is the worst case time complexity, is big O of n square. So in this way we calculate the time complexity for different scenarios, like when we have consecutive statements, when we have loops, when we have nested loops. We will also see some more guidelines, but we will see them in the next lecture. Okay friends, this is it for now. Thank you for watching this presentation.